Hi guys, this is Faizan and welcome to today's session on understanding hashing algorithm. Now before I start, can you guys quickly confirm in the chat if I'm audible or not? Can you see me? Can you see the pointer over here? Can you see the slide deck as well? If everything is okay, just quickly write in the chat yes so that we can get this session going. Okay. Okay, while we wait for others to join, let me give you a quick tour of how our academy looks like. So just go into your Google Chrome or any browser. Just type in Great Learning Academy, the first link that is there. Just click on it. It will redirect you to this page. Now here you can see that there are different tabs over here. Career path. If you're looking for a career change, or you're looking how to proceed in data science, we have options for data science, artificial intelligence, machine learning, cloud computing, and marketing and finance. If you're looking for career transformations from different universities, we do have programs with them as well. So we have programs in data science and business analytics, AI and machine learning, management, cloud computing, cybersecurity, and software development as well. Plus design thinking is also there. Okay, so if you're looking for something that is absolutely free, right, now we do have courses available, free courses available as well. So if you go in here, you see we have IT and software. What are the courses available which are absolutely free are data structures and algorithms in Java programming is there, Python for beginners is there, ethical hacking, cybersecurity, HTML, CSS, JavaScript, data structures. All these courses are absolutely free. And if you're looking for something that is in Hindi, we have courses available in Hindi as well. We have Python programming in Hindi, machine learning in Hindi, Java programming in Hindi, C programming, C++. All of these courses are available, and all of these courses are available for free. And if you want to get a certificate, right, you just need to answer 6 questions correctly out of 10. If that is done, yeah, you will get the completion certificate. Okay, with that being said, okay, cool. So now let's get started with our session. So today we are going to understand hashing algorithms and what is hashing. Okay, why do we do hashing? So what are the things that we are going to cover? First, we are going to see what is an algorithm, and then we will see what is hashing. Then there will be several problems that we will discuss. So basically we will discuss two problems, okay, based on hashing. Okay, so prior to that, these sessions, right, before these sessions, before this session I have also taken a session on greedy, right, backtracking. Greedy is there. D and C, that is divide and conquer, is there. We have also arranged this session on recursion as well. So do check these sessions once the session is over in order to get the idea of how backtracking algorithms work, how greedy algorithms work, how divide and conquer algorithm work. We have a separate sessions on these algorithms or types of algorithms that are there, or programming paradigm, you can say. Okay, so now with that being said, let's see what is an algorithm. Okay, yes, so you're audible, we can see the screen. Okay, great. Okay, so now what is an algorithm? Basically anything that you write which is absolutely independent of programming language constructs. Okay, so it is absolutely, or you can say it is independent of any programming language, and it can be easily understood by a non-technical person, right? And it is a crisp solution, or you can reach to a crisp solution. Basically, if there's a problem, you can write many algorithms for it. Let's suppose one algorithm. In this algorithm, you're taking time complexity of n square. Okay, next time you saw, okay, this is the thing that I'm doing redundantly. So what you did, you just rephrased or reiterated through this entire algorithm, and you changed it from big O of n squared to big O of, why big O? This is basically the worst time complexity we are talking about, worst case time complexity. Okay, you change it to big O of n log n. Then you say, okay, I can do something else. If I'm using some extra space, maybe I can reduce this time complexity to big O of n. Okay, so this is how you reach to a crisp solution. So depending upon your algorithm is nothing but a step-by-step approach, or step-by-step steps that you take to solve a particular problem. Okay, now there can be multiple algorithms, like you have seen, one can take n square, one can take n log n. So depending upon these algorithms, you can reach to a crisp solution which is most efficient, or the one which is having reduced time complexity and space as well. Okay, so this is whole what you can, in a nutshell, you can say what is an algorithm. Okay, now this is about algorithm. Now let's talk about hashing. What is hashing? So basically, hashing is something which is used so that your time complexity, that is the operations like insertion, right? Your insertion is there, your deletion is there, your searching operation is there, right? All these operations can be performed in a constant amount of time depending upon what your hash function is. So hash function is nothing. We will talk about what a hash function is, how you can write an efficient hashing algorithm, which is not possible because there will be something that is known as collision, which we'll talk about. Okay, so that will be always there, and we try to reduce that collision. Okay, that's it. Okay, so now hashing means that you will be mapping your data, and basically not data, your data will be mapped in terms of key and value. Okay, so let me just clear out the screen, and let me just write in this. Okay, cool. So now let's suppose you have an array. Okay, and now you have memory locations, and you have a stream of numbers. Let's suppose 21, 23, 24, then you have 11, then you have 15, then you have 16. Okay, so you have these numbers, and now what you did, you have one hashing function. We'll talk about this hash function more and more. Okay, is there a paid course on DSA? uh, uh, yes, Raghvendra says, is there a paid course for data structures and algorithm you're talking about, Raghvendra? Okay, so now you have these stream of numbers, right? And what you can say that, okay, we have a PG course available on especially in software engineering. Maybe you can find this DSA over there. Okay, so now what you have a stream of numbers, and now what you have a hash function, which is basically dividing, which I have written, and it is not that much efficient. What I'm doing in that hash function, basically I'm having this number and I'm doing a modulus by 10. So what I'm doing, this is my hash function, and every time when number comes, I will divide it by, or I will do a modulus operation, and I will divide this number by 10, or we can say I will mod this number by 10, and what is the remainder that I will get 1. So if I'm doing a mod operation on any of these numbers, the result will be always from 0 to 9, right? It is quite simple, right? So you have these many memory allocations, or these many locations wherein you can store these numbers. So what hashing does, it uses the concept of what, can we get a certificate for all the free courses in GL? Yes, Vidya, yes, those will be a completion certificates. Okay, for all the free courses. Okay, so now you have this number, and you just map it with this memory that is over here, and the remainder is 1. So you will write over here, you will write 21. Okay, you will write 21. So next time, let's suppose 23 comes, and you will if there is a third location, and you will write 23 over here, then fourth, and you will write 24 here, because the remainder is 4, and so on and so forth. Now when 11 comes, now you see, when you do a modulus of 10 by of 11, you do a 11 mod 10, you will get a remainder 1. What is this 1? Basically this 1 will go into this location, and you will see, okay, we already have a number that is 21 over there. So this is what is known as collision. Okay, so this is what is known as collision. So collision is nothing when, please provide separate course for DSA. Sure, there is already a course, Raghvendra, there's already a course on data structures and algorithms are on our YouTube channel. It's a 10-hour course. Okay, you can check it once the session is over. Okay, cool. So now this happens when there is a collision. What do you mean by collision? When you already have a number that is 21 that is already present at this location, and the next time you have a number that is 11, and you have a hash function which is also resulting in 1, and but there is already a number present. So this is what is known as collision. So now collision happens when you're trying to insert a value, and that value has been already occupied some other value. At that time you have certain resolution techniques that you can have. Okay, so now the most simple is that you can have this, obviously this is from 0 to 9, and then you have 21, 11, and 20, let's suppose 41. Okay, so now at this location you have a linked list. A linked list is created, and this is known as open hashing, because this is open hashing because you're not performing, you're using an external space that is outside this memory location. That means you're using a linked list, and you will be storing in such a way that 21 is here, here you have 11, then you have 41. But now what is the drawback of this open hashing technique? right? You will create a linked list obviously, but the problem is that let's suppose you have a number which is 51, 61, so you end up having a linked list which is elongated on this position, and rest of the array or rest of the locations are empty. So now how to resolve this problem is by using linear probing or quadratic probing or double hashing. All of these fall under closed hashing. Because the time complexity to reach a particular position or to search an element will be, because you're using a linked list, so it will be big of n. That is not the objective of hashing. The main objective of hashing is to reduce the time complexity, so it takes more memory. Yeah, you can say that obviously it will take more memory, but the main issue is not the memory, is that the operations that we perform, operations, right? These operations that we are performing, insertion, deletion and searching, these will take these operations will take a lot of time, right? If you're searching for a number or you're trying to insert a number, obviously it needs to travel to the end and then insert the number. So the whole objective of using a hashing was to reduce this insertion time complexity, reduce the deletion time complexity and searching complexity as well. So that objective is lost, okay? And plus we are not having these elements distributed all over the memory. That is also a drawback over here. But what is the resolution is that we can use closed hashing. So one such technique is linear probing, second is quadratic probing, and third is double hashing. So again, these are, all of these are what? Collision resolution. So collision will be there no matter how efficiently you have written this hash function. Okay, you might say that, okay, now time complexity 2, sir. Yes, Kashyap. Okay, so no matter how inefficient your hashing function is, collision will be there. Or you can say that you will write a hash function which is basically it's a numerical expression. No matter how basically here what I was doing, I was having this key, that is the element, and I was doing a mod operation with this 10, right? So this is my hash function, simplest hash function, right? You can have you can mod it by 100 so that you can have 0 to 99 locations wherein you can store this, right? That is not the case, right? That is not the objective here. What I'm trying to say is that no matter how efficiently you have written your hash function, collision will be there. And obviously the better hash function, the less collision, but it will not be the case that it will never have collision. Collision will be there, okay? So now these are the techniques with which you can resolve those. So we have already seen open hashing. Now linear probing, what it does, you have this location wherein you are having numbers from 0 to 9 wherein you can store this. So now you have a 1 and this was 21. So 21 took this place. Now next time 31 came, okay? Next time 31 came. Now linear probing, what it does, it searches for the next open position. So he went on here, okay, he sees that, okay, this position is already taken by 21. What he does, he linearly probes. That means he linearly searches for the next open position next to 21. Yes, but obviously now Shrishti. Okay, so what Shrishti is saying, that it will have a much more space complexity, but there is how to overcome collision. So yeah, Vidya, that's what I'm trying to explain here. Okay, so just give it some time and I will explain all those things. Okay, so yes, there will be a extra space complexity, but it is always asked, or it will be always there, that you have to do a trade-off. That means either give priority your time complexity or your space complexity. So always we'll see some problems how we are doing this trade-off in this session itself. So basically, how you are prioritizing your are you prioritizing time complexity? Do you want to be time efficient or do you want to be space efficient? So there always be a trade-off. So mostly what we do, we have systems wherein we have lots of memory available, so we tend to ignore the space. But if you have an examiner which is explicitly asking for you to not to use extra space, at that time hashing is not the best way, because you will be including or you will be having some extra space. We'll see the problems as well. So now how to avoid this collision. So earlier what we were using a linked list, and that was called as open hashing or chained hashing. Okay, so now what is this? These are closed hashing, and that means we are performing everything in this particular location. And now what happens, now every time when we have a collision, it will linearly look for the free space. Okay, so it will do a probing that is linear in nature. So it will check, okay, is this position empty? Yes, so it will place 31 here. Now next time what it comes, when it comes, and it will check again. So it will check again, okay, is this empty? No. Is this empty? So he will insert 41 here. Next time 51 comes, he will check linearly one by one. So again, you see the time complexity to insert is again getting in some kind of a big O of n, right? Order n. So now next time what we thought, okay, now this is not working much more efficiently, as also you might be having chunks of memory available free. So let's suppose you have a chunk of memory that is allocated in this. That means we don't have a distributed elements all over this array. So now let's suppose we are talking about, this time we are talking about 10 locations. Let's suppose we are talking about 20 locations, for example. Okay, so you have 5 elements over here. So next time what you have, let's suppose this is a not a 20. So let's suppose you have elements over here, 1 2 3, anything, right? So you have elements over here as well. So these chunks will be occupied, and the rest of the chunks that is over here and over here, these will be free, right? So if we want a balance in both time and space, then so if you want a balance, then what you can say that try to I will show you an example wherein we are reducing our time complexity from big O of n square, then to n log n, then finally to n, and how we are doing a balance between the both. Okay, just wait a second. I have a problem that is in this session itself. I will talk about it and I will explain each and every step how we are doing that. Okay, Srashti? Okay, cool. So now we don't have these distributed elements all over this memory location. So what we do a quadratic hashing. So instead of linearly searching, we do I square. That is this, if this is a second collision, so I means the number of collisions. So we have a hash function, let's call it h of x, and then what we are doing, we are multiplying it with I square. That is quadratic. We are making it a quadratic function kind of a thing, and we are multiplying this hash function that is here. So this hash function can be, let's suppose, as simple as what, you have a key and you are doing a modulus by 10 plus I square. Okay, so this I is the first, this will be the I means the number of collision. So this is the first collision, then we will do 1 square, second collision 2 square. So with this, what we are doing, basically we are distributing our elements. Now our first element will be here. Next time when a collision happens, this 20 will be over here. So there will be a space of elements. So we are distributing our elements all over this array. Okay. So similarly, we have double hashing. We will use 2 hashing functions. Let's suppose we have one hash function h of x, and then we have one more hash function that is h1 of x plus some quadratic multiplication. We are doing it. Okay, so that we can again so obviously the problems in this quadratic hashing was that we were not able to distribute that much. We were distributing elements, but not that much. We still had some spaces or chunks of memory available here and there which are free, which were not utilized. So double hashing helped in that as well. So these are all the collision techniques and how we can resolve it. Okay, so this is not the objective here. So we are trying to understand what are the different types of hashing. Now let's see why we do this hashing. So basically, obviously, the best hash function, if you have, the operation will take constant amount of time. Constant, okay? So searching, constant. In linked list, if you're trying to search, you need to traverse the whole linked list, right? That is not the case in over here. If array, if you don't know the index, again, you need to traverse, okay? If you want to search something, if you're using a linear search, again, big O of n. So all these operations will take constant amount of time, if and only if you have a best hash function, okay? So what are the properties of best hash function? So what should be there in a hash function? It should be computed easily. Okay, we should have this hash function which is computed easily. Okay, we should have less number of collision, or you can say a best case scenario where we don't have any collisions. We should have that hash function, and we should distribute our elements uniformly, which we talked about, linear and quadratic. So we can have we can just build something based on these things what we have learned, right? This linear, quadratic, and double hashing. We can build our own hash function. Now we are not going into that how we can build that, because that is humanly impossible. Okay, so what we depend on some of the inbuilt hashing functions that are already there. So if we use a hash map, right, in Java, so there's already a hashing function which Java has already provided us, and obviously we know now how he was if he's having a better hash function, what are the things that he should keep in mind. What Java might be keeping in mind is that it should be computed easily, no collision or less collision, or distributed uniformly. So we know how he can distribute it. He might have be using a quadratic not a quadratic or double hashing if you want to distribute these uniformly, and number of collisions will be also less in double hashing. Okay, and it should be written in such a way that it should be simpler to compute. Okay, so these are all the things. Now all the operations will in at a, if you're talking about the average time complexity, all these operations, now why I'm saying average, because it depends on your hash function. Okay, so we assume that Java gives us the hash function which is absolutely perfect, which will not be the case. There will be some scenarios which is wherein it will not be perfect, and we will have some collisions. Okay, let's assume that it is perfect, and in the average case, the time complexity of performing these operations, insert, delete, and search, will be constant, big O of 1. Okay, so what are the applications? Now let's talk about the applications. Whenever you're trying to count the number of occurrences at that time, that, or you can say the frequency of elements at that time, you can use this hashing. Okay, finding the occurrences or the single occurrences of elements at that time, when you're trying to find the distinct elements, we can use hashing. Okay, it can be applied for numbers as well as strings. If you're trying to find the replicates, that means how many elements are repeated how many times, at that time you can use this. Okay, for removing the replicates from a particular string or a particular array, you can use this. So these are all the simple applications. Obviously it will depend, or it will vary from application to application. So these are simple examples. Okay, simple applications. Now let's talk about our first problem that is there. Okay, so now let's see how we can use this hashing. Obviously we are going to use something that is already available for us, that is Java has already provided us some hash function that is absolutely perfect. Can you please explain in C++? So this gist will remain same, Vidya, but here what we are using Java. So you try to convert it into Java, or try to convert it into C++. Okay, so now what we are going to use, we have this example, so you can understand the example and then try to implement it in C++. Okay, okay, so now quickly confirm, guys, can give me a quick confirmation that everything was so far, everything was, you understood everything. Give me a confirmation. Quickly, guys, just write a yes or a no. Do you want me to repeat anything? Quickly, guys. Thank you, Abraham. Quickly, guys, we can then proceed with this problem, and I will show you how to do a trade-off, how to reduce your time complexity, and how to use this hashing, how this hashing comes into picture. Okay, okay, great. Okay, so I don't see many responses, so quickly respond, just write a yes or no. If you want me to repeat, that is also okay, I'll repeat it. Okay, so now let's see, the first problem statement is that a subarray with a sum equal to 0. So you have an input array that is 6, 2, 5, 4, 5, 1, 5. You need to find a subarray that is there. Subarray means that it should be contiguous. So this is a subarray. Okay, it's not that you are picking one element from here and one element from here. This is not a subarray. This subarray should be contiguous. So that means one after the other. Okay, so this is a subarray. 6, 2 is a subarray. 5, 4 is a subarray. Also 6, 2, these are also subarrays. Okay, so all of these are subarrays. Okay, so let's clear the screen, and you need to find the array which is difference between open and closed hashing. So obviously now you can see easily the differences, that open hashing means that you are utilizing some extra space. That means for chaining you're using the linked list, right? Obviously there is caching that is there, that comes into picture, the performance comes into picture. All of those things are there between if you are trying to compare the open hashing and the closed hashing. Okay, so obviously there will be much more what you can say collisions in open hashing as compared to closed hashing. Okay, right? So 0 rocks. Okay, so there are many differences. These are just simple differences that we just covered. Obviously the number of occurrences of collision that will be there are much more. Okay, subset of the main array, sir. Subset, yes, you can say that, but yeah, not yes, you can say that it should be a subset of the main array. Okay, You can say that, but it obviously depends from your problem to problem. At that time, sometimes he might say that, okay, now subset will also include 5, that means null. That is not the case, that is not the subset over here. Okay, that is that there is no such array as 5, that we have a sub array named as 5. Okay, so that you need to keep into this these sub or you can say the edge cases in your mind. So this is not a exactly subset. Okay, so now what is the subarray? So in this array, that is 6 2 5 4 5 1 5, there is no such array whose sum is equal to 0. But if you take this example, now if we don't have, we return 0. If we have 1 2 1 and then we have -4 and then we have 1 and 6. So if you talk about this subarray, when we calculate its sum, that means it will give us a sum, and this subarray, the sum of this subarray is 0, so we will return 1. Okay, so you see the question. So question is to find the subarray whose sum is equal to 0. Now there can be a lot of questions, they can be asked a lot of questions. When I say lot of, there can be n number of questions that can be asked on this same problem. So here we are talking about a subarray whose sum is 0. You might say that sum is equal to k. So k can be anything, right? So you can implement those things on your own. Okay, so now let's see the first solution that comes up into our mind. Okay, so what we were going to do, you have I'm writing just the function. This is just the function. Okay guys, so now what you're doing, you have this array 6 2 let me just pick the same array, 6 2 5 4 5 1 5, 6 2 5 4, or not this array, rather let's pick up the array which is having some subarray. Okay, so now let's take an example over here, this example. So 1 2 1 4 1 6, or 1 2 1 4 1 6, that's -1. Okay, cool. So this is the array that we have, and now what we are doing, what we have, first loop, that is this this flag is just to represent, okay, we are having some now we have that subarray, we have found that subarray. It can be anything, it can be temp, it can be anything. So now we have this flag that is used for the indication. Okay, and what we are doing, we have this iterator I that is starting from this location. Obviously we will have 0 1 2 3 4 and 5, these are all the indexes. Now yeah, so now what we have, let's change the color. Okay, so now we have this iterator I over here, and we have the sum that is used to calculate the sum. Okay, and we have a j which starts from I, that means currently it is from here, it is on I, that is I and j should be at same position, starting from the same position. And then what we are doing, we are traversing and calculating the sum. So what we are doing, we are doing sum equal to sum plus a of j. A of j is 1, so sum will be 1. Now we move ahead, and then what we do, we first check, is the sum equal to 0? Is sum equal to 0? No, it is not equal to 0. So we move ahead. So what we do, we added 2 to the sum, because now j is over here, and we added it, we made it 3. And then what we check, is sum equal to 0? No, we added 1, we have 4. Now j is over here, we have 4, we check, is sum equal to 0? No, sum is not equal to 0. We added we moved across, we are in this inner loop, guys. So that is why I'm incrementing only j and not the I. Okay, so what is happening, one by one we are adding it and checking the sum. So at this position, let's suppose we have this -4 right over here. So what we are doing, we added this to this, right, this sum, and we get the sum as 0. Now we check, is sum equal to 0? Yes. Now here your flag comes into picture, that identification, that unify, that flag that we have. Okay, now it is set equal to 1, and we break out of this inner loop. Okay, and then we check if the flag is equal to 1. Okay, if the flag is equal to 1, yes it is, that means we are breaking out of this for loop as well. We will not move ahead. We have found we have that particular subarray which is having a sum 0, and we don't care about all the elements that are there. Obviously that can be a question also, that you need to find all the elements in that particular subarray whose sum is equal to 0. That can be the question as well. Okay, but now here we have simplified it. We have simplified it such a way that we are just looking for true or false. So now we have returned, and we break out of this loop and we return the flag. Now flag is 1, that means yes, there was an array whose sum is equal to 0. Simple. Now let's let's consider the scenario wherein we don't have such thing. So let's suppose this is +4. Okay, so now what we are doing, 1 second guys, so let me erase these things over here. So now let's do one more thing. we have the sum. Let's remove this sum as well, and let's remove this flag. So you can implement it any language, guys. So this is something that has obviously you can implement it, or you can use dictionaries, right? So now you have this array. This is a 0. Sorry for the noise. Now what you have I over here and you have j over here, right? And you have this flag. Obviously this flag that is used is 0, right? And now what you're doing, you iterate one by one. You check for this, you check for, okay, is this sum equal to 0? No, it is not equal to. Sum is equal to what? 1 plus 2 plus 1 equal to 4, 4 plus 4 is 8, 9, and then 15. Sum is 15 over here, okay? So now once you are iterated through this entire for loop, okay, so entire for loop is done, then we check, is flag equal to 0? No, it is not equal to 1, right? Flag is still 0, so we are not breaking out of this loop again. Then we increment our I, and now we are having this I from here, and now instead of going from this position, this is already done, okay? Now we iterate j from here to here, okay? So now if you observe carefully, this is the most naive way. That means this is the most brute force way, and the time and space complexity associated in this problem is that the time complexity is big of n square, right? That means because you have a one for loop that is iterating from 0 to n, and inside that we have a nested for loop which is also iterating from 0 to n, okay? So when this is the scenario, then we mean that m into n might be having some idea about time complexity. So this is the scenario of m into n. That means this is taking n and this is taking n, so that means n into n, which is nothing but big O of n square. So this is taking a big O of n square time, and the space associated with this is nothing but constant, okay? So now this is your first approach. Now this is a brute force approach. Now the question is, can we do better? Can we do better? Can we use something and reduce this time complexity? Yes, we can. So now what we are doing, we are going to implement this thing with the help of hash set, which is something, if there is a set associated with it, that means this is something which doesn't allow us to enter duplicate values, okay? So now what we are doing, we are using this hash set, and we will store all the elements that are present in this. So now how would we do that? How would we reduce our time complexity, and we will increase our space by n, because we are going to store all the elements or some part of the elements in this hash set, okay? At worst we can store all the elements, so that is why the space is n, okay? Space complexity is big O of n. So we declare hash set like this in Java, okay? And now what we are going to do, we are first going to add 0 in the hash set. So we have a hash set over here. Now this is the beauty of Java. So he has implemented his Java has JVM has already inbuilt that hash function which he has already there, and so all the operations that we do, we perform insertion, deletion, will take constant amount of time. So this is how we reduce our time complexity from big O of n squared to big O of n. That means linear. So that means if we had earlier 1000 operations, that means we have 1000 operation, we will take 10 raised power 6 units of time will be required. But now in this case, if we have 1000 operations, it will take only 1000 operations, right? Yes. So if we talk about million into million operations will be there, right? It will take million into million time complexity. It will take only million, right? So you see the drastic change in the time complexity just by using or implementing this hash set, okay? So we add the 0. Then what we do, we let's suppose we now what we do, we have the sum, okay? We have the sum that is used to calculate. We just inserted this hash set equal to, we inserted 0 in this hash set just to check, okay, if the sum is equal to 0, we already have that 0 already present in that hash set, so we can just return 1 or 0, that's it, okay? So now what we do, we calculated, we added up. Now you see we are using this this is another for each loop that we have used. You can also use a simple for loop, that is not an issue, okay? So one by one we are traversing. So we have reduced, or we can say that this is a efficient way to write a for loop. You don't have to specify the end condition, the condition and the updation. It will automatically update itself, and it will automatically traverse to the end of the array, or you can say the length of the array, okay? So now what we are doing, we are traversing one by one through the elements, and elements will be here. So in our case, what was the array? 1 2 1, and then -4, and then 5 6, okay, whatever, okay? So this was the array. One by one we are adding these elements to the sum. So 1 is there, we added it to this, and then we checked if set dot contains this sum, this sum is already, if one is already present in the hash set, so contains, we are searching. Okay, so again this is a constant operation. Okay, so now yeah, for each, yes, Abhishek. So now what we are doing, we are checking for this sum if this is already present in the hash set. No, it is not. So what we are doing, we are adding this sum in the array. Okay, in the hash set, so 1 is added. Next time what we do, we have this 2, we added this 2 to the sum, we checked, okay, is this 3 already present in the hash set? No, we added this sum in the hash set. So next time what we have 1 again, we have this 4, we added this 4 in the hash set, and the next time we have -4, we added this to the sum, and we get we added this, when we added this, we get 0, and we checked, is this 0 already present in the hash set? Yes, it is. So this is how we were able to find that element only by traversing single time. We will not be traversing now again next time. So we are using only a single loop. That is how we reduced our time complexity from n square to n. You see, just by using this hash set. And but what we have to keep this thing in mind, that if for example this -4 would not have been there, so we will keep adding all the elements unless and until we are at the end of the array. So we will return at the end, we will return 0, which depicts that we don't have any we don't have any such subarray in the array which is having the sum 0. Okay, so this is how we use this hash set, and we reduced our time complexity from big O of n square to big O of n. But this time around, this was the time complexity, right? And if we talk about space complexity, earlier we were using constant amount of memory, and now in the worst case we can use all the elements. Just we have seen that if there was no such array, so we keep adding all those elements in the hash set, so the time complexity will be big O of n. Similarly, the space complexity will be big O of n. How hash map increases the size? Please explain properly. How hash map increases the size, sir? Okay, so you're talking about the space complexity. Okay, so now when you talk about space complexity, Ureva, okay, so I'm sorry if I'm not pronouncing it correctly. Okay, so yeah, so when you're talking about space complexity, you keep two things in mind. What? The number of elements that are present in the array. Okay, so now let's suppose you have 1 2 3 4 5 elements present in the array, and you are using one temporary array which is in which you are again storing these elements. That means 1 2 3 4 5. This means that you are using an extra amount of space, which is nothing but big O of n, where n represents the number of elements. So now if you observe carefully, in the earlier example, in this example wherein we are talking about the space complexity as n, right? So basically what is happening, we are using this hash set, and in this hash set we are inserting elements, and although we are not inserting the same elements as in the array that was there, right? 1 2 1 -4 5 and 6, we are not implementing the same array, but the number of elements, that means we are talking about here 6 elements, the insertion in this array, in this hash set, is that we are inserting 6 elements, right? If you observe carefully, we have 0, then we had 1, then we had 3, and then we had 4, then we had again the 0. Since it does not allow duplicate, so 0 will be again there. So let's suppose if this 0 wouldn't if -4 was not the scenario, if -4 wouldn't be there in the array, so at that time what you will write, 8, and then what we will have 13, right? And sir, can we have time as constant for this problem? You cannot, you need to traverse one by one. Okay, so I can skip, I can reduce the space complexity. Vidya, I can reduce the space complexity to constant, but since we are trying to understand hashing algorithms, we will use this extra space. So if you want to reduce this extra space, we will use the, because we are talking about hashing. Okay, so if you want to reduce this space, we can use the operation that is XOR. So if you do the XOR of all the elements, you will get that not here. Okay, so you have this, you are looking for, no, you can reduce its space complexity, you can try it out. Okay, so since we are using this hashing, so that's why I'm sticking to the extra space. Okay, so obviously you can do better. Obviously there will be some algorithms which can do better or perform better than this algorithm. Okay, so since we are only checking out, or we are only trying to understand this hashing algorithm. So that is why we are opting for this hash set. Okay, you can perform, or you can have any algorithm which might perform well, or you might do anything which will not be the case. You can perform, you can have a algorithm which will, you can, in which we can do in it in a constant amount of time. So not, no, you cannot do that in constant amount of time. Okay, so obviously you can have a better algorithm, like you can, I don't know, I'm not for sure, I haven't tried it, but you can try it and you see if there is an algorithm which will perform better, right? Like when I mean better, maybe you can see it in a log n time or anything like that. Okay, without using any extra space, we can try it out. Okay, so this is all about this problem. Let's move on to the next problem. Okay, so yeah, where was I? Yeah, so you will see that all the elements will be, the 6 elements will be inserted in this hash set, or moreover 7, so which boils down to what? Big O of n. Okay, cool. So now let's move ahead and let's see this next problem. What is the next problem? Okay, so now here what we are using, we are having an array. In this array, what we have, okay, what we have, we want to find the element that is repeated only once. All the rest of the elements are repeated twice. Only one element is in this array which is not repeated twice. So you see the 1 is repeated twice, you see 3 is repeated twice, 5 is repeated only once, 6 is repeated twice. So you need to find that element which is not repeated. So it is a constraint, the one constraint is there, that all the elements will be repeated twice and only 2 times, not more than 2. And there will be only one such instance where the element will be only once. That is, this will be the scenario. It's not that you might say that, okay, so will it work for 1 is 3 times, 2 is 2 times, or 4 is once, and 5 is 5 times. So that is not the question. The question is simpler. Let's keep it simplified. So because I want to focus on something else at the end, so I'm sticking to only I'm sticking only to 2 occurrences, because I want to implement it in a constant amount without using any extra space at the end. But if you don't want that if you don't want it to implement in a constant amount of space, that means you don't want to perform it in a maybe order n and constant amount of space, then you can say that, okay, this can be the scenario. Since I want that constant space to I want that constant space at the end, so that is why I'm opting for 2 occurrences. Okay, so I will tell you why I'm doing so. So now if you see this example again, 10 is repeated twice, 30 is repeated twice, 60 is repeated twice, 50 is only once, so 50 is the answer. So this is your problem statement, simple, right? And now what is the first approach that comes into your mind is that you're going to use 2 nested for loops and you will perform this operation. How? You will see, okay, you will have this array. Let's suppose we have this array 10, then 20, then 10 again, then 30, then 20, and that's it. Okay, so you have this array, for example. Now what you're going to do, you have a nested for loop. So one is iterating from here and another is iterating from j to n. So for every for this 10, you will be checking, okay, is this 10 with the help of this j? Is this 10? Okay, no. Is this 10? No. Yeah, is this 10? Yes, it is. So you will see that, okay, this 10 is repeated once. Is this 10 is repeated twice? So 10 is 2 times. Okay, now next time what you do, you update your I, you will check for 20. Is 20 this? No. Is this 20? Is this 20? Yes, it is. So 20 is also 2 times. So you will check for 10, which is already checked. Okay, so because since we are always iterating from 0, so we will always check from this 0th index, because every time our I starts from 0 to n, but our j always starts from 0 and keeps checking to the n. So next time again from 0 to n. Okay, so that is why, and we are keeping this condition that I and j should not be equal, because that will be the case when you are checking for the same element, right? I is also there, j is also there, and you are saying that, okay, it is repeated twice, but that is not the case. It is the single occurrence, right? So that is why this condition is there, and we are checking for the rest of the elements. Okay, so now if we have exhausted entire array and there is no such element, we will return nothing but 0, or you can say that we don't have any such element. Else if we have such element, we will just print out that element, that is a of I, which is in this case will be 30. Now obviously I'm not focusing that much on this approach, because this is again a brute force approach, right? That means brute force means straightforward. Okay, brute force means straightforward. You're using two loops which are iterating from 0 to n, and the inner loop is also iterating from 0 to n. That means the time complexity of this problem will be big of n square. Okay, and the space complexity is constant because you're not using any extra space over here. But if you do this problem, or if you solve this problem using this approach, you will not get selected. So what is the better approach, or you can say the second approach that you can use? You will say, okay sir, since I know there will be only two occurrences of these numbers, so what will I will do, I will just check for this, I will just sort this. So you will write 10 10 20 20, and or you can say the 10 10 20 and then 30 30. Okay, I will just sort this array at the starting. So you will use arrays.sort, which is a which is there in Java. You can use that, or you can use any sorting algorithms like bubble sort, simplest sorting algorithm, that is bubble sort, or you can use a complex one, that is merge sort. So obviously depending on whatever the sorting algorithms that you have used, your time complexity depend on that. Because after this sort, when you are once you are done with the sort, you just iterate through this array, and that's it. You will check, okay, is this location and this location same? Yes, it is, right? And then you move ahead. If these are not same, then you will stop and you will break out of that, and you will print that. You will check, okay, is this 10? Yes, it is. You will move ahead two times. So you will check, is this 20 and this 20? No, here this is 20 and this is 30. Okay, let me just write it bit nicely. So you have this array over here. You have 10 10, you have 20, and you have 30, and you have 30. You have sorted it. Okay, so now what you are doing, you are just iterating through this loop only single time. So that is why the time complexity is big of n. Okay, so now why I'm saying this is n log n, I will tell you in a minute. Okay, so what I'm doing, I'm checking a of I and a of I plus 1. So are these two elements same? Yes, it is. So this will not be executed. We will move ahead two times, right? So earlier I was here, now I is over here. So we will check, are these positions same? No, these are not same. So that means this if statement will be executed, and we will print a of I, which is nothing but 20. So 20 is the element which is not repeated twice. So we'll print it and break out of the loop, because we know there will be no such instances where this will be the scenario that 20 is already once, or you can say that there will be no such element like this. So 50 is there, and it is also repeated only single time, because I have already given you the constraint that all the elements will be repeated twice except one. So this is that one. So why to move ahead? So just break out of the loop. Okay, so done. But you might be thinking, okay sir, since we are traversing only n times, or in the worst case we are traversing only n times, why we are saying the time complexity is n log n? Okay, so why? Because the time complexity, the time that will be taken by this sort method, that is this sorting that you perform, and you are doing an internal sorting internal sort that is already given by Java, which uses merge sort. So the merge sort in worst case takes n log n time complexity. So this is n log n plus big O of n. So this is m plus n when you talk about time complexity. So you will always go for the one that is higher. So why higher? Because as soon as your input changes, right, you're talking about million inputs, right? You're talking about million square inputs. At that time this term becomes negligible. Okay, so you'll always talk about the greater terms. Okay, so that is the reason the time complexity of this will be n log n. So now if you're not using this internal sorting algorithm that we have in Java, if you're using a simplest sorting algorithm and like bubble sort, at that time the worst case time complexity will be n square. So this will change from n log n to n square. Okay, so you should rather go for something that is much more efficient. You might implement it in merge sort or quick sort. Okay, both of them will yield n log n in the worst case. Okay, so you should go for those two algorithms. Okay, so now the complexity has been reduced. So earlier we had n square, and now what we have, n log n. So we have reduced our time complexity from first approach to second approach. Now the question is, can I do better? Can I do better? Yes, I can. At the starting, if you observe carefully, when I was trying to explain you the algorithm, I just gave you the hint, right? At the problem statement, I wrote something which is kind of a map, right? So I will be using a map over here. So I will be using a hash map. Obviously, we will declare this in this fashion. We will declare a hash map in Java. So we have a hash map like this. This will be the key. and this will be the value. Okay, so now what we are doing, we will map, or we will try to create this map first. So what we will do, we have this 10, we'll write its occurrences. Okay, so we will iterate through the array once. So this is for the n. This is the time complexity that we will take, that is big O of n, and we will iterate through all the elements only once. Okay, so now what we check if map dot contains key. That means, so at the start this is empty, right? So now we are checking if this 10, that is the first element that is present over here, so it can be 10, 20, doesn't need to be sorted. Okay, so 10, 20, then we have 30, then we have 30, let's suppose 30 is at here. Okay, so 30, 10, 20, 10, 30. Okay, so now we have this array, so we check, is this 30 already present in our map? No, it is not. Then go ahead and insert it. Okay, so what we did, we put 30 over here, and in the key in the key we put 30, and in the value part what we did, whatever we get over now over here. No, okay, wait. So now this is not present in the key, right? So we go into the else part and we inserted this 30, and along with it we inserted this value, which is 1. So this will be executed if it is not present in the map. Okay, so let me just clear it. 1 second, guys. Can find my pointer. Yeah, so now this 10 is done. Okay, so next time around what happens, now we are talking about this 10. Is this 10 already present in the key, already present in the map? No, it is not. So what we do, we insert 10, along with it 1. So this is only inserted once, so or the occurrence of this 10 is only once. So next time again same thing happens, we check for 20, 20 is also once, then 10 comes. Now we check, okay, is this key already present in the map? Yes, it is. So go ahead and override it. So we again write 10 over here, but this time what we did, we first fetched this value, that is this 1, and then increment, that means map.get whatever is the value, we fetched it, which is 1, and 1 plus 1 is 2. So we insert 2 over here, and similarly we go for 30 and we do the same, we override it and we fetch the previous value and increment it by 1, and that is 2. So this is our map, and this whole thing is done with the help of this for loop over here. Okay, we created our map successfully. Okay, done. So let's erase everything. Now we have our map over here, which is 10. It can be in any order. Okay, order is not important. Okay, so 10, 30, this is twice, and this is our map, this is our key, this is our value. Okay, so this we did in big O of n time. Okay, so now what we are doing, now we are checking for that particular instance where the value is 1. So what we do, we extract all the key sets. So one by one we will be extracting 10, 20 and 30. We will be extracting these key set, and we will checking whatever is the value associated with this key, please check. Okay, so we get map.getX, that means get the value of this 10, which is 2. If this is equal to 1, that means this is that element, break out of this loop. In the worst case, we can find that at the end. So again, we will be iterating big O of n times. So these are individual. So again, we are talking about m plus n. So big O of n plus big O of n. So which boils down to big O of 2 times big O of n. Obviously, constants will not take part in the time complexity, so we can neglect this too. So the overall time complexity will be big O of n. Okay, done. So now what we'll do, coming back to this, we'll check. Okay, is this value 2? No, it is not. Please move ahead. Check the 20s. Get the value associated with this 20. Is this 2? No, it is not. Get the value associated with this 30. Is it 1? Yes, it is. We find out our element and we return this. We printed out this 30 because this is, or not 30. So yeah, here it is 20. Okay, so you have 30 over here. Here we have 20. We printed out this 20 and this is our value. Okay, done. So this is how you iterated over this. And now you're using this extra space over here, which is big O of n in worst case. Okay. So in worst case, you can have a big O of n extra space and the time complexity will be big O of n. So now in this way, we have reduced our time complexity from big O of n square to n log n and then finally to n. But over here, we were using constant space. So we used n space over here in order to reduce this the time complexity. Now the question is, can we do better? Yes, we can neglect this. We cannot use this extra space and still we will be able to find our answer. That is with the help of XOR operation. In this case, if you do XOR of all the elements, that means XOR of 10, 20, 30 and then 20 again, then 10 again. If you do XOR of this, you will get 30 as your output, because XOR is one such property which if you do an XOR of A and A, it will yield in 0, and if you do an XOR of A 0 and A, it will yield you A. Okay, so XOR of 10 and 10, again it's 0. XOR of 20 and 20, it is 0. So you will be XOR of 0 0, and XOR of 30 will yield in 30. So you can neglect this extra space that you're using, and you will be performing this in a linear amount of time without using any extra space. So space will be constant. So this can be done, but since we are trying to understand the hashing algorithm, so that is why we opted for this hash map over here. Okay, so this is it from this session, guys. I hope you enjoyed this session as much as I did. So if you have any questions, you can post them in the chat, as we will be concluding this session. Okay, so you might be thinking, okay sir, we reduce these time complexities one by one. Okay, so this is how you perform, how you write different algorithms, and how you reach to a conclusion, or how you reach to an efficient algorithm. So first we had this in n square, then we reduced it to n log n, then we reduced it to further n, and then finally we used extra space over here, and then finally we can also do it in n without using any extra space, right, with using a constant amount of space. Okay guys, so thank you so much guys. If you don't have any questions, if you have any questions, you can put them in the chat quickly, guys. So you can implement this in C++ on your own, guys. So you know the algorithm, you know what to use and how to implement this. So now go ahead and implement it in any language that you want. It can be C++, it can be Python, it can be any language, JavaScript as well. Okay. Guys, quickly confirm. If you don't have any questions, then we can just drop off from this session, and do practice a lot, guys. Practice is very important. You need to practice, and only then you can deduce these algorithms, or you can reduce the time complexities in this manner. Okay, so you need to think of the problem, and you need to then evaluate these things. Then can I use this? First write it in the brute force, then try to reduce it one by one. Then try to write or use the extra space, or then try to remove the extra space, and then see what happens. Okay, so you need to do these kind of things in order to reduce the time complexity. Okay guys, I see that you don't have any questions. Thank you so much guys. Thanks a lot, and I'll be concluding this session. Thanks a lot.